I've got a new supply of chocolate, so it's, if you've been saving up your questions, this is the time to ask them. Let me just find the notes. Yeah. So let's just review quickly what we found last time. We found that the first order correction trying to get these things organized here. Well, it's certainly true that the first order correction to the energy of the nth level is simply, this is for non-degenerate perturbation theory, is simply the mean value of the perturbation in the nth level. And on the other hand, the first order correction to the state is a projection operator that projects onto everything except n0 divided by En0 minus H0 times the potential times n0. And then we found that delta 2 and was the sum k not equal to n vkn squared over En0 minus ek0. And writing this would be a sum over k not equal to n, and it would then be a k0, and then a k0bn0, which we could call vkn, and then it would be divided by En0 minus ek0. So that's the first order correction to the state. And what I should say is that although that's the first order correction to the state, there's a lambda in there, in that the state n is n0 plus lambda n1. So that's how it looks. And also the change in the energy En minus En0 is lambda delta n1 plus lambda squared delta 2. Okay, so that's our review of the non-degenerate perturbation theory, and we want to apply that to an example. And the example, I've got so many notes here, all sort of mixed up. Right. So we were doing the quadratic Stark effect on the ground state of hydrogen, and sure, I need some more. And so here what we've got is we have H0 is P squared over 2mu minus E squared over R, so that's the problem we can solve. And then the potential V, or rather lambda V, is EEZ. So it's just an electric field in the Z direction. And now as we look for the lowest order correction over here, we see that actually vanishes because 1, 0, 0, Z, 1, 0, 0 is 0. That's because this 1, 0, 0 state is perfectly symmetric, and Z obviously is plus at positive Z, negative Z. And so we're going to then to the second correction, and if we use this formula over here, we see that the second order correction, D2100, is then E squared, and what I actually see is that we sort of lapsed in the notation here. In other words, we sort of absorbed the lambda squared into the delta. Anyway, so this is the actual change in the energy. We don't need to add lambda. This is actually lambda squared, delta squared. Is E squared times the sum, n not equal to 1, all ln m, nlm z100 squared divided by E10 minus En0. And because this is hydrogen with its atomic hydrogen with its hidden symmetry, the Ln dependence is not present. Okay. And just to remind you, can you see when I write? See when I write here, I guess. En0 is equal to minus EI, the ionization energy, over n squared, and that's equal to minus a half mu c squared alpha squared over n squared. So that's the that's what we have to compute. Now the electric dipole moment D is, for any state psi, is minus ER inside. Here we're taking E to be positive. There are two conventions. One, E is positive, the other one, E is negative. I think the E positive convention is winning, but anyway. We now look at our expression over here for what n is. We see that this n will be n0 plus lambda n1, and that's going to be n0 plus lambda. The projection operator for everything except the n state, En0 minus H0 N0, so that's just recapitulating what we had there. And so this state psi is then 100, the ground state of atomic hydrogen, and then it is plus EE sum n not equal to 1, all ln m, NLM, Z100 ground state, and we're dividing by E10 minus En0, En0 being this expression here. Is that a question? All right. Okay, so now we have to take the matrix element of D in this state, and so what we get is D is equal to, and so it would be, I'm going to write as a big bracket here, 100 plus E sum n not equal to 1, and then it's going to be 100 Z NLM E10 minus En0 minus ER and then over here we're going to have 100 plus EE sum, maybe I should say n prime not equal to 1, L prime, n prime, n prime, L prime, m prime, n prime, L prime, m prime, z 1, 0, 0 over n1, 0 minus n0. Okay, so that's the expression. And the biggest term would come from the 1, 0, 0 diagonal element. That's 0, so that's gone. And so then what we have is the cross term of z and e1, and then the other term, the other cross term, 1, 0, 0 minus er, and then all of this. And what you can see is that that just contributes a factor of 2, which somehow escaped from my notes. So there's a typo in my notes. I mean, just okay. So let's look at some of these. We now need to evaluate these matrix elements that are here. The Z1 and then the R between 1, 0, 0 and NLM. So first of all, NLM Z 1, 0, 0. What about this? Well, there are various ways of thinking about it, but let me give you a fundamental way of thinking about it. You can stick in here NLM, you can stick in the identity in the following form. E to the I theta J3 over H bar, e to the minus I theta J3 over H bar, Z 1, 0, 0. This is a rotation about the z-axis by angle theta. When it hits z, it doesn't do anything because z is pointing in the z direction. When it hits a spherically symmetric state, it doesn't do anything. So this has no effect. On the other hand, this one on this one is e to the I m theta over, in fact, not even over h bar because it's an eigenstate. This is an eigenstate of J3 with eigenvalue mh bar. And so this is e to the I m theta times mlm z1, 0, 0. As this goes away, it doesn't do anything. So now we have that this is equal to this for arbitrary theta. So you said, so if m is not equal to 0, you can just set theta equal to pi over m as an angle, and then you get e to the I pi times this thing, which is minus this thing. So we have that this is equal to minus itself, and then you add this to both sides, and you get twice this equals 0. So this thing is equal to 0, NLM Z 1, 0, 0 equals 0 for m not equal to 0. There are other ways of seeing it. In the notes you have a simpler description, but it's better, I think, to think of these more fundamental ways of looking at things. Now, what about x and y? Well, the same thing could be said for x and y. Well, let me give you the other way of looking at x and y. X and y are proportional to linear combinations of y1 plus or minus 1. So if you have something like n Lm x 1, 0, 0, this is spherically symmetric, so this whole thing is proportional to y1 plus or minus 1. So that then tells you that if this is an m, this effectively is m equal plus or minus 1, then m here, if m is 0, you're going to have no contribution. And so this is going to be saying that n, in fact, just nl0, x100 is 0, and also nl0, y100 equals 0. If you wanted to do these in a different way, well, it would be a little tricky, actually. I suppose this is the easier way to do this. All right, are there any questions about that? Remember, I do have trouble in my right pocket. Okay, all right, well, let's take this matrix element then and see what we get. What we get then, in particular, if we write E as D times Z hat, then what we're going to get is, first of all, that, let's see, this one over here says, this one says that M has to be 0. So then if M has to be 0, the X and Y is going to vanish. Okay? So in other words, we have a, maybe I should do this more slowly. What we have here is 100Z or NLM. NLM R 100. Okay. This condition over here says that this is going to be 0 unless M is 0. So that tells me the only thing survives is 100Z, NL0, NL0, R100. But then these relations tell you that because this is 0, the X and Y go away. And so this goes down to 100Z, NL0, NL0, Z100. So this means that the only component of R that survives is the Z component. And that's why B is proportional to Z hat. And moreover, once this happens, you see that this is just the absolute value squared of 100Z NL0 squared. So this thing that starts out looking fearsome and complicated because of these, I guess, orthogonality relations or selection rules, collapses into something very simple. And the something very simple then is that the magnitude of the electric dipole moment is minus 2 E squared E. So note, one factor of E from here, one factor from here. And of course, I'm neglecting the inner product of the complicated sum R complicated sum. That's more complicated to evaluate, but it's higher order in E. It's proportional to E cubed. And E is a small number, so we can neglect that. Oh, there's something else that I have to say here. And there's another selection rule. So I'm going to write this as an L to begin with, because that's as far as we've gotten. E. Okay, so that's our sum at this point. Our formula for the electric dipole moment. Now, let's imagine actually doing this integral. Well, this is a spherically symmetric function. And so the angular integral is going to be d omega, which means, of course, d phi sine theta d theta. This is going to be a Legendre polynomial. In fact, it's just PL. In fact, when this is the peak, let me write this as an integral dx from -1 to 1 and d phi from 0 to pi. And it's going to be PL of x because m is 0. This is going to be P1 of x, and that's it. So the d phi just contributes 2 pi. Now we have an integral from -1 to 1 of PL of x with P1 of x. Well, these things were orthogonal polynomials, Legendre polynomials. And in fact, you can construct the Legendre polynomials, curiously enough, by just saying, taking the polynomials x to the n and requiring them, these polynomials x to the n, of course, are not orthogonal. But you say, well, let's apply the Graham-Schmidt process, the Graham-Schmidt orthonormalization process to these polynomials and make them orthonormal at the interval -1 to 1, which is the integration of the unit sphere. And that gives you the Legendre polynomials. Normalization and everything. Anyway, so this tells us that this is proportional to delta L1. So this L here is only 1, so I can get rid of this L. So this is a simpler expression. So it's just a sum over the p states. Are there any questions? Okay. All right, now it's a matter of computing all of this. So what is E1 minus E10 minus En0? We're always running out of blackboard space, so I'm going to use this space here. E10 minus En0. This is going to be minus a half mu c squared alpha squared. 1 minus 1 over n squared. And so this expression then for d, well, there's something else here. We're going to write d. We're going to say that d is chi times E. Obviously, the strength of the electric field is not a fundamental property of the hydrogen atom. And so it makes sense to define the dipole, the magnitude of the dipole moment, as the linear electric susceptibility times the electric field. And so our expression for chi just means you cancel the E, strictly capital. So the electric susceptibility then, when we take into account this factor of 2 and that factor of 2 and the minus sign, minus sign here cancels that minus sign. Okay, so anyway, you guys can do your arithmetic better than I can. Mu c squared alpha squared sum n greater than 1 n1 0 z1 0 0 squared over 1 minus 1 over n squared. Because one of the things that has hypnotized physicists for, actually it's almost 100 years now, is that these energy levels of hydrogen go as 1 over n squared, where n is an integer. And that means you can approximate things pretty well, apart from the fact that it's means that you have to do quantum mechanics rather than classical mechanics. Anyway, this quantity alpha is dimensionless. It's e squared over h bar c. And if we substitute that in there, then let me skip one line in the notes because it will take us too long. 4h bar squared over mu e squared, sum n greater than 1, n 1 0 z 1 0 0 squared over here, 1 minus 1 over n squared. All right, the next point is to say, well, we don't really need to compute this thing. You can get an upper bound on this. And so what we do is we say 1 over 1 minus 1 over n squared is less than or equal to 1 minus 1 over a quarter. In other words, n equals 2. If you go to n equals 3, then this thing becomes closer to 1. Yeah, that's right. No. Well, let's see. As you take n to infinity here, this goes directly to 1. And this is, well, that's right. This is 3/4, so 4/3. So indeed, 1 is less than 4/3. Yes, this is 4/3. Somehow I'm not thinking clearly. This is, of course, 4/3. And this one, for n equal to 1, of course, it's infinity. For n equals 2, you have equality. But for n equals 3, it's 1 minus 1/9. So it's 8/9. So it's 9 over 8, which is less than 4 over 3. All right. So what we can do then is we can approximate, we can get an upper bound for this sum. And the upper bound then is that we can say pi is less than or equal to 4h bar squared over mu e squared, 4/3 sum n greater than 1, 1 0 0 z, and I'm going to write this in a long-handed way, but there's a reason for that, because so now we've just replaced this by 4/3 and pulled out the 4/3. Now you see, we're just looking for inequality, so we can add other intermediate states here and increase the size of the right-hand side, and we'll get a weaker inequality, a weaker upper bound. And so we can say this is less than or equal to 16 over 3 h bar squared over mu e squared. But now it's the sum, not simply over n greater than 1 and L equal to 1 and m equal to 0, but we can say it's over all n Lm. N, y. All n Lm. 1 0 0 z n Lm n Lm z 1 0 0. And all these terms are positive because they're just the absolute value squared of 1 0 0 z n Lm. But now this is the identity operator. So this is less than or equal to 16 over 3 h bar squared over mu e squared 1 0 0 z squared 1 0 0. All right, now for goodness sakes, ask a question. This illustrates some of the nice things that can happen in now we have the calculations to reduce something that would be hopelessly complicated to something fairly simple by using the completeness of this and replacing the sum over dyadics just by the identity operator. Of course, the fact is that in order to get from here to here, I have to toss in also the continuum states. All right, now this is, eventually, of course, we have to do an integral. We can't just fool around with general principles all day long. So we have to do an integral at some point. So let me, just to conserve board space, start over here. What is this 1, 0, 0, z squared 1, 0, 0? Well, obviously it's a third 1, 0, 0, r squared, r vector squared 1, 0, 0, because the ground state of hydrogen is spherically symmetric. Okay, well this one is just simply 1/3. Remember, the spherical harmonic part of the hydrogen atom wave functions are themselves separately normalized over d omega. And so all we have to do is integrate over r, 0 to infinity, r squared dr, r10 squared of r, and now r squared. So this is the volume element, this is the r squared that comes from here. And that is equal to 4/3, the Bohr radius to the minus 3/3 power. That comes from the normalization here of r10. Integral 0 to infinity, dr, r to the 4th, and then this r10 squared, which contributes e to the minus 2 r over a0. So now we let x equal 2r over a0 and change variables, and this turns into a0 over 2 to the 5th, because we've got 1 here and 4 there. 4/3 a0 cubed in the denominator. Integral 0 to infinity dx, x to the 4th, e minus x. Of course, is a famous integral, and it gives you 4 factorial. And so altogether then, this thing is 16/3 h bar squared over mu e squared times, well, I should actually put the 4 factorial here. So this is a0 squared over 2 to the 5th, 4/3, 4 factorial. And now, if you work that out, everything cancels, it turns out, except for the a0 squared. So this gives you a0 squared. And so this is a0 squared. And in fact, this is a0. So this is 16/3 a0 cubed. And that's about 5.3 times a0 cubed. The exact answer for chi1s, the ground state electric susceptibility, is 4.5 times a0 cubed. So you see, this is a pretty reasonable, a pretty good approximation. In other words, it's an upper bound indeed, but it's much better than an order of magnitude. It's off by, I think it's off by less than 20%. Okay. So, and I guess how could you have done it better? Well, it would not be that hard, for example, to compute this for the p equals 1 state, so say for the, where was I going to do this? Do this for do it exactly for n equal 2. And, well, I don't know. I thought I saw a way of approximating it a little bit better, but I'm not sure. Okay, so that's the quadratic Stark effect in hydrogen, ground state of hydrogen. Are there any questions? All right, the next topic is degenerate perturbation theory. We already did, frankly, about as much about degenerate state perturbation theory as you find in most textbooks. But I'm going to try to give you a description of the degenerate case that's a little better than that. It turns out this is not a complete description either. The degenerate state perturbation theory can really be a mess. So we're going to, you remember what I told you was the basic way of, let me review what we're going to be doing for degenerate state perturbation. So we have H equal to H0 plus lambda B. And the question is, what do you do for, what do you do in non-degenerate perturbation theory? Well, in non-degenerate perturbation theory, you just say that the mean value, you just write down the nth level, the mean value of the Hamiltonian in the nth level is n0, H0 plus lambda B n0, and this gives you En0 plus lambda n0 B n0. So that's what you do in non-degenerate perturbation theory. It's really mass, isn't it? But now in degenerate perturbation theory, what you've got is several different eigenvectors of H0 that have the same energy levels. And so what you do effectively is you instead of having N0, you then have N0I. And so you can imagine that the eigenstates, the lowest eigenstates of H are going to be, how shall I write them? In N1, well, I'll write them in here as L0. And they're going to be a sum on, they're going to be a linear combination of all of the states. In other words, we have G sub n states that are degenerate here, these N0 comma I, such that H0 on N0 comma I, they're all E N0, N0 comma I. So that's the degeneracy. And so this thing here is a sum, I equals 1 to G sub n. G sub n is the degeneracy of the nth level. And so then we just write the eigenvalue equation, and this eigenvalue equation is simply, let us say, H on L0 is going to be ENL L0. And now when L0 acts on this, you're going to have H0 plus lambda B acting on the sum here of N0I, N0I, L0, and these guys are all going to give a value of En0, and then plus lambda v on this sum N0I, N0I, L0. And so if we just subtract E0 from both parts, we're going to say then that the NL1 contribution on L0 is going to be lambda V from here N0I. I did this last time, I'm just sort of reviewing it. L0. And now taking the inner product from the left, with respect to, say, N0I, what we get is E1 NL N0I L0 is lambda V N0I L0. Whoops, well, that was a big mistake. This obviously is an operator. So this really is lambda N0, well, it's got to be a K. N0K V N0I N0I L0. So it looks like that, and of course we still have a sum over I. Okay, so this is an eigenvalue equation then of the form lambda V Ki L times N0I L0 is equal to E1 and L N0 K L0. So this is a matrix equation then that this is supposed to sum over I. So this is that this lambda times the square matrix V times this column vector L0, say, is equal to E1 and L times this column vector L0. This is what we worked out before. So the first thing to do then is to diagonalize the square matrix and find these separate eigenvalues. And so that's the first order degenerate perturbation theory. Now, there are, of course, two cases. One is that this perturbation V is sufficiently asymmetrical that it completely breaks the symmetry in the symmetry of H0, at least for the nth level, and so that you get as eigenvalues here from this G by G equation, you get G different eigenvalues, so you completely break the symmetry. Then there's the other case. The other case is you don't completely break the symmetry. And in the case where you don't completely break the symmetry, you're kind of stuck. And you have to, I don't know of any way of really, I don't know quite how to proceed, although the method I told you last time where you just truncate the system to some n by n system, compute all the matrix elements laboriously, and then just apply linear algebra and diagonalize H. That of course will always work, but it can be extremely laborious. So we're going to assume for the rest of this treatment of degenerate state perturbation theory that we're dealing with a level and a potential such that this procedure here breaks the degeneracy and gives us, in other words, instead of having Gn eigenvectors all with the same energy, En0, that we now have Gn levels L0 So L0 black hole. L0 should have, well, L0, where L goes from 1 up to Gn, and these energies, E and L, are all different. So you have G different, G sub n different energies. Okay, so that's what we're going to be talking about. Another way of thinking about this is to introduce a projection operator onto the set of these are the set of eigenvectors of H0. So, in other words, we have H0, N0 is E degenerate 0, N0. So these are the G sub n degenerate eigenvector, degenerate states. So we start out with these G sub n degenerate states, and we have a projection operator onto this subspace. And what I described here as kind of a tangent is the procedure of diagonalizing P0, V, P0. In other words, we truncate the operator, the potential V, just to the subspace spanned by these Gn degenerate states. We call this Vd. Not to be confused with medical condition. All right. Now, there's another projection operator that we're going to be talking about, namely P1, which was the identity operator, minus P0. And now, is that a projection operator? Well, you know the rule for a projection operator is to square it. So P1 squared is 1 minus P0 squared. And so that's 1 plus P0 squared minus 2 P0. But P0 is a projection operator, so P0 squared is P0. So this is 2 minus 2 P0. Wait a minute, I've got this wrong. So, this is 1 plus P0 minus 2 P0, so this is 1 minus P0, which is equal to P1. So in other words, P1 squared is P1. So P1 is the projection operator onto the space that is not everything except the space spanned by the degenerate states. So this is another projection operator. Now what we want to solve is the equation 0 equals E minus H0 minus lambda V L. And we imagine that as lambda goes to 0, this state L is going to go to L0, L0 being the eigenstates of this truncated potential. All right, is that clear what we're doing? This gets worse. I'll just tell you, this gets to be very complicated. And the amazing thing is that if we don't have the case where all the levels of the are in other words, where the potential removes the degeneracy by virtue of its asymmetry, the thing is, this method just completely breaks down. So what we're going to do is we're going to write, we of course have the rule that 1 is equal to P0 plus P1. And so we're going to take this identity operator and stick it right there. And that's going to give us the following. It's going to give us 0 equals E minus H0 minus lambda V times P0L plus E minus H0 V P1 L. And now, let's notice that H0 P0 is equal to ED P0. And so we can, so when the H0, let's see, what am I saying? Right. When this H0 here just hits a P0, so it's effectively, and rewrite this as E minus the common degenerate energy minus lambda V P0 L plus E minus H0 minus lambda V P1 L. Okay. Now we can use the projection operators to split this one equation into two equations. And so we're going to do that in a second. Just see if we get a drink here. All right, let's notice a couple of things. First of all, let's notice that P0 times E minus H0 times P1 equals 0. And why is that? Well, that's because the states in this is the sum over dyadics, and this is the sum over dyadics. Let me just write down what P0 is. P0 is the sum m in the degenerate level, m0 cross m0, and P1 is the sum of all the other, let's say, n0 cross n0, and not in this displaced energy level. So these guys are completely orthogonal to each other, so P0E P1 is certainly 0, but P0 E0 is ED times P0, and so this is also 0. In other words, this thing is equal to minus P0 H0 P1, which is minus ED P0 P1, which is 0 because P0 times P1 is clearly 0 because the states here are on states. Okay. Let me just see where I am. So far we just have this equation. Just that. Okay. So now what we're going to do is we're going to multiply this equation from the left by P0. And when we do, what we get is 0 equals E minus ED. I have a 0 now in my notes, ED 0, but I don't think that's necessary. Minus lambda P0V, P0L. And then over here, this term and this term, let me write it as two equations, plus P0, E minus H0 minus lambda V, P1L. So that's just multiplying this whole equation from the left by the projection operator P0, which slides through these numbers and hits there. When it hits here, so P0 squared is P0. But now this one goes right through here. P0E P1 is 0. P0 H0 P1 is 0. So this just leaves us with 0 is equal to E minus EG minus lambda P0V P0L minus lambda P0V P1L. Okay, so this is a somewhat simpler equation. Now, we're going to multiply this equation from the left by P1. And first, we're going to notice something. Namely, H0 used with P1, because P1 is just a sum over diagonal over dyadics of eigenstates of H0. and this is rather hard. I'm proving it in a different way. 1 minus P0, so this is minus H0 P0, and we know that's 0. And so when we multiply this equation from the left by P1, what we get is that the P1 hitting E minus ED and then hitting P0 gives us 0. So we just get 0 equals minus lambda P1 V P0 L. And then we have a P1 here, and but for these two terms, there's already a P1 here, so that just gives you P1 squared. So this one just changes by E minus H0 minus lambda P1 V P1 L. Okay, so that's the second. So we have two equations now. This one, which we could call equation 2, and this one, which we can call equation 1. So we've got this eigenvalue equation, we split it up into two separate equations. Okay. Now, let me just illustrate which one we're dealing with. As I said, this is pretty confusing. All right. What we're going to do is we're going to take the second equation and we're going to say that we can invert this operator. Now, why can we invert this operator? Well, it's sitting with a P1 here. So we could, in fact, insert another P1 there gratuitously, because the only thing, that just makes this P1 squared. And that's no different since it's a attraction operator. Now, what does this tell us? This is the Hamiltonian, but with the P1 on both sides. And because it has the P1 on both sides, it's only the states that are not in the degenerate level. And so the eigenstates here are going to be, there's going to be a big gap, because all the eigenstates of this operator are essentially separated by the splits between the degenerate levels. Okay, in other words, we have Gn levels here, and maybe Gn prime levels here, and Gn double prime levels up there. The splitting between the sets of degenerate levels is big, and that's what is in here. So we can invert this. And when we invert it, what we get is P1L is equal to, so we just multiply by this operator inverse on both sides of the equation, and what we get is that this is equal to this divided by that. And since there's a P1 here, we can multiply by an extra P1. So we have a P1, we have a lambda over E minus H0 minus lambda P1 V P1. Now times this over here, which is P1 V P0L. Okay, so that's our expression for that. And that's a little more complicated than we need. But anyway, what we're going to say then is that L is equal to L0 plus lambda L1 plus dot dot dot. And so, yes. So P1L is just P1 is going to give 0 on that. So this is simply lambda P1 L1. And P1 L1 is effectively then from this equation, this is going to be P1 lambda over E minus H0 P1V, P0, L0. So in other words, we keep this, but we're going to toss this out because this would only contribute order lambda squared. So more simply then, we've got that P1, L1 is the sum K not in this degenerate energy level, K0, K0, V, L0 over ED0, I don't know if we need a 0 there, anyway, over E minus K0. In other words, we've inserted here what actually P1 is, and P1 commutes with H0. So this thing, once you express P1 as the sum over K0 dyadics, this thing simplifies quite a bit. So that's actually the hard part of the thing. And equivalently, we can write this as a sum K naught in V, K0, VKL over ED0 minus K0. Notice that this is connecting states K that are not in the degenerate level to states L in the degenerate level, or to the state in the degenerate level. The state that diagonalizes, the state that we found in first order degenerate derivation. And now we want to find P0L. And so what we do is we take this equation here and we put it into equation 1. In other words, this equation here. So we take that and we put it in there. In other words, we substitute for this right-hand side here. And when we do, we get a pretty complicated equation, keeping in mind, though, that P1 and P0 are orthogonal. What we get is 0 equals minus lambda P1V P0 L plus E minus H0 minus lambda P1V P1 L. I'm sorry, I completely screwed up. I copied down the wrong equation. We substitute we get something much more complicated. 0 equal particles. What we're getting is E minus ED0 minus lambda P0V P0L minus lambda P0V P1 lambda over E minus H0 minus lambda P1V P1 P1V P0L. Okay, so in other words, we're substituting this expression here into equation 1 over here on this side. And so we repeat all of this, which was there. And then we repeat this structure, but then P1L gets turned in, becomes of that form. So that's our expression. And now we can see that we've got a P0L as a common factor. So we can write this as 0 equals E minus ED, or ED0, minus lambda P0V P0 minus lambda squared P0V P1 1 over E minus H0 minus lambda V P1V P0 all on P0L. Sorry. Obviously, we're going to ignore that in a moment. Now, if we look at this to order lambda, well, then we get rid of all this complexity, and we just have the very simple equation 0 equals E minus ED minus lambda P0 is P0 on P0 L. Well, this is just the lowest order equation that we were solving over there and that we solved on Monday. So this just says that the lowest order, the eigenstate in this subspace, is just obtained by diagonalizing the potential within the subspace. Okay. Now we're going to approximate this equation by using the eraser to, obviously, we don't want anything of order lambda cubed in here. This thing's complicated enough. So we just get rid of that. Because, 1 over something plus epsilon is 1 plus epsilon lambda cubed. Okay, we have this equation. And let's suppose that the eigenvalues of this, the eigenvectors of this equation are L0I. That is to say, P0V, P0 on P0 Li0 is VI P0 Li0. So these are these eigenvectors that we were finding over there and finding on Monday for degenerate state. In other words, this is the square matrix. This is the eigenvector. That's the eigenvalue. Then these eigenvalues E1 are ED or ED0 plus lambda VI to first order. Now what we're going to do is we're going to effectively apply non-degenerate perturbation theory to each of these levels. And the way we're going to do that is we're going to say that we have a script V. So this effective script V potential is the thing we find in here. This script V potential is going to be lambda squared P0V P1 1 over ED0 minus H0 P1V P0. So that's this structure here. And this thing is going to be already H0. So this is going to be E minus H0 effectively. In other words, script H0. Script H0 is going to be the ordinary H0 plus lambda P0 V P0. All right. So now what we have is effectively an expression for, we have non-degenerate perturbation theory for each of these distinct levels split by this operator. And now we have, this is our potential, and this is our known Hamiltonian. And so what we use is that the first order direction is what I call P sub n over En0 minus script H0 V, script V on N0. And this P sub n is the sum J not equal to I, Lj0, Lj0. So this is a projection operator within the subspace, but on states that are just different from the ith one. And so then that tells us that P0 Li1, using this expression, is the sum, oh my goodness, we're just about out of time. We're out of time. J not equal to I, lambda squared P0, LJ0, LJ0, V, P1, 1 over ED0 minus H0, P1V, Li0, and there's also a factor over here, which is ED0 plus lambda VI minus ED0 minus lambda VJ. All right, so this is sum J not equal to I, lambda P0, LJ0, LJ0, V P1, 1 over ED0 minus H0, P1V, Li0. And let me write it one more time. P0, Li1 then is the sum J not equal to I, lambda P0, LJ0 over Vi minus Vj, sum K not in D, LJ0 V K0, 1 over D0 minus K0, K0 V LJ0. All right, so that's, I think we've got to stop here because we're sort of at the end of the hour. We're way at the end of the hour. Are there any questions? Remember, I've got all this chocolate. This, frankly, I find very complicated and hard to follow. So, and also, as I said to you, it only works if the degeneracy splits, if the perturbation completely splits the states in the degenerate level. Anyway, it's basically all in the notes. So we have we have now a break because I'm not going to be here next week, and then when I get back, I'll try to finish this, and then go on to do some applications. I put the homework on the web page. If you think the homework is too difficult, let me know. But I think in the problem that is, well, I don't know, just send me an email and I'll give you hints. I did put some hints. And one of the problems, which is very long, there are many parts. There's an easy part and a hard part, an easy part and a hard part, an easy part and a hard part, an easy part and a hard part. So, without working very hard, you should be able to get, without even thinking, you should be able to get half of the hard, half of the long problem.